Can you hear me?
I can hear you. Can you hear me?
Oh yeah, we can. Very nice, very nice. Thank you so much. I was talking to my colleague Vipin Kumar from computer science, and he mentioned that you are probably one of the top researchers in climate modeling in the world. So it's really an honor to have you, sir, here. Yeah, thank you.
Thank you very much for a very warm welcome. I'm going to talk to you a little bit about the state of the art as climate scientists understand it for understanding what's going on with the planet and what the prognosis is for what will happen in the future, and delve briefly into what the implications of that will be for both ecosystems, society, agriculture, and industry. So we know that the planet has changed over the last century. We can go pretty much anywhere in the world where there was ice and where we have records of ice. This is a photograph of the Medenhall Glacier in Alaska taken in 1894. We can go to these places, we can find the records that were taken, say, 100 years ago or longer. And we can go back to those same spaces and see how things have changed. This is taken in exactly the same place. As you can see, the landscape has radically changed. And this is true pretty much everywhere you go, whether it's in the Rockies, Glacier National Park, the Andes, the Himalayas, the Alps, glaciers in Africa, in Papua New Guinea, all the way around the world. These glaciers are in pretty much full retreat, and in many places have totally disappeared. In Greenland, where there are obviously even larger glaciers, we now know that the ice sheet is losing around 250 gigatons of ice every single year. In Antarctica, we know that West Antarctic is losing hundreds of gigatons of ice per year. And thankfully, the East Antarctic ice sheet seems to be quite stable. All of these things are demonstrations that the planet is not in equilibrium. It is not standing still. We can see the impacts as well in the Arctic, places that are particularly vulnerable to sea level rise, places that are particularly vulnerable to increased erosion as sea ice in the Arctic retreats. And the sea ice has decreased by over 30% over the last 30 years. And this is a picture from Shishmaref, which is on the Bering Sea in Alaska. And what you're seeing is a town that was built on sand, literally. But when they built it, it was frozen sand, protected from the waves by the ice. The ice has gone, the waves have come back, and the permafrost has melted, leading to erosion rates along the coast of tens of meters of coastal erosion per year. And that means that towns like Shishmaref are completely unviable. Obviously, this house and the ones behind it are all gone. So if we know that the planet is changing, how do we quantify that? Well, we have good data. We have good data that goes back to the 19th century, where we can put together an estimate of what the global mean temperatures have done over that period. So there's a lot of information in this picture, or one similar to it. You can see there's ups and downs, from year to year. Those are part of the normal dynamic weather of the planet. Whether there's an El Nino event or a La Nina event in the Pacific has a big impact. If you look closely, there's impacts from big volcanoes which cool the climate for a few years if they go off. But what you can see, I think, quite clearly is that over this period, while there have been ups and downs and periods where things don't appear to be happening, the overall trends are very clearly up. And the trends are so clear that 2016 was by far the warmest year on record, going back at least to the 19th century and possibly for hundreds of years, perhaps thousands of years before that. The different colored lines that you're seeing there are different estimates, different groups independently trying to estimate how these changes have occurred. And you can see there's a pretty large overlap of those different estimates. So how you estimate the global mean changes is actually not that important. You get basically the same result either way. But now let's look at how big this change is, right? The scale on the left is in Celsius, so it's about a degree Celsius since the end of the 19th century, and as you know, that's about 2 degrees Fahrenheit. Is that an important number? Is that something that we can just measure, but it doesn't really have any impact? Well, the answer is no. This is actually a very large number when it comes to the temperature of the planet. We already saw that ice is responding very clearly to the temperature changes that we've already had, such that glaciers are in retreat almost everywhere in the world. But let me give you another number that puts this change into perspective. This 2 degrees Fahrenheit that we've seen, this rise. Minnesota can get quite cold in the wintertime, as I'm sure you're aware. But of course, 20,000 years ago, Minnesota was completely covered in an ice sheet. That ice sheet was part of the glacial interglacial cycle, the last big ice age that we had. That reached its maximum size about 20,000 years ago and started to retreat subsequently. Those changes associated with the coming and going of those massive ice sheets are driven mainly by the relatively slow changes in the orbit of the Earth. But the global mean temperature change that's associated with that change in the ice, and remember, the ice sheet stretched from New York to the Arctic Circle, from Spain to Scandinavia. The amount of water in those ice sheets reduced sea level by almost 400 feet. The temperature change associated with that was only about 8 or 9 degrees Fahrenheit colder than the pre-industrial period. So when people say, oh, it's only been 2 degrees Fahrenheit, what they're actually saying, it's about a quarter of an ice age unit, right? So if an ice age from the pre-industrial was 1 ice age unit in the cold direction, we've gone a quarter of an ice age unit into a warmer future. And the projections that I'll show you a little bit later put us in the potential situation of being 1 full ice age unit in the other direction. And the ice age, I'm sure you don't need to be reminded, was a completely different environment and a completely different planet for ecosystems, for agriculture, which didn't exist, for sea level, for infrastructure. So what we're seeing so far is A, measurable, and B, not ignorable. But the big question that people ask us is, well, how much of this is because of us? How do we do this attribution of climate change? How do we understand why things are changing the way they are? Now, attribution is fundamentally a modeling problem. Now, whether you're using a statistical model, some kind of empirical fit, whether you're using a complex physics-based model, you always need to have a model that says what would have happened without us. And obviously that's a counterfactual. We only have one history of the real world. And so you need to be able to predict what that change would be. And that has to be credible. We do have tools that are capable of doing this now. So these tools are called climate models. What you can see here, hopefully this animation is coming through. What you can see here is the output from a climate simulation. The colors that you're seeing are the different components in the atmosphere. Orange is dust being lifted from the Saharan desert there. Blue, swirling in the storms in the North Atlantic, is sea salt being lifted up by the winds at the sea surface. White, you can see wispiness coming from Europe, and as the Earth turns, you'll see more in China and India. That's sulfate pollution, sulfur dioxide coming from the burning of relatively high sulfur coal, producing sulfate particles and other kinds of pollution. The red dots that you see are fires that produce soot and other organic aerosols that you can see in the green. The two like the dots you're just seeing going across the screen there, those are tropical cyclones, and obviously the winds are very strong in those, and so they lift up a lot of sea salt into the atmosphere. I'm showing you this animation because I want you to see that the climate and the weather systems are complex, and we understand that they are complex. What you are seeing as well is that things that go into the atmosphere are affected very dramatically by the weather patterns, the storm systems that you can see around Antarctica. You can see a volcano just about to go off just north of Madagascar. And volcanoes are obviously a natural phenomena that also puts sulfur dioxide, a cooling agent, into the atmosphere. But what you can also see is that all of the things that we are doing, the deforestation, the burning of coal, the burning of oil, changing patterns of land use, all of these things themselves are affecting the climate. So they are being moved around by the climate and affecting the climate itself. It's a very, very complex feedback that goes between all of these different factors. And really the only way to understand it is to put all of these things in together and allow that complexity to work its way through. But we do have these tools. So the question, though, is, are these tools skillful? Do they tell us things? Do they make better predictions than simple alternatives that we might, write on the back of an envelope or cobble together with an Excel spreadsheet? And the answer is yes. And I'll give you a couple of examples of how these model skills actually are demonstratable and therefore give us credibility in the predictions that they make for the future. So here is a model of the temperatures over the 20th century compared to observations over the 20th century. What you're seeing in these early years, the blue and the yellow coming in and coming out, are really just weather. So you don't expect the weather to be correlated between the models and the observations because weather, as we all know, is not predictable too far in advance. But as we get towards the end of the 20th century and into the 21st century, we see something else emerge. We see a large-scale warming pattern that looks very similar in the observations in the model. Warmer over land than the ocean, warmer in the Arctic than in the tropics, and the least warm in the oceans surrounding Antarctica. This is a fingerprint of change that, as you can see, the model captures very well. So the model does provide some skill. This is better than you would have got just by guessing or just by doing a simple calculation. The interesting thing about the model is, though, we can now break down why that is changing. Those simulations over the 20th century had all of the different things that we think of as having changed over the 20th century that are important for climate included. And so now we can break those elements out and we can ask ourselves, what is causing this pattern to change? So here is that temperature trend that I showed you early on. And so we can ask this question, what caused the planet to warm? I mentioned orbital changes. They're very small on this period. We can look at solar changes, the cycles in the sun. We can look at the volcanoes, and you can see that the big volcanoes have a noticeable effect on the climate. But if you look at all of the natural changes together, You see a huge discrepancy between what was observed and what we would predict. And so, what of the human impacts? Land use, chopping down of forests, but planting crops, ozone pollution, aerosols, which actually are a cooling effect, and of course greenhouse gases from the burning of coal, oil, and natural gas. So greenhouse gases would have actually warmed the planet more than we've actually seen. But if you combine all of the human impacts, there's a little bit of cancellation, and actually the long-term trends are very close to what we observe. And of course, if we include the natural and the human impacts all together, we actually end up with a match to the observations that is pretty much as good as we could expect. So when people ask us, why has the planet warmed? Who's causing that change? Is it a natural cycle? The answer is no. The reason why the planet has warmed is because of us. It is our activities dominated by the role of fossil fuels in producing carbon dioxide. Though that isn't the only thing that's going on, as you can see. Now, here's where the models really come into their own. Because if we had observations of the future, we obviously would trust them more than models. But unfortunately, observations of the future are not available at this time. And of course, that is always going to be true. And so if we want to make predictions, we have to have models, and we have to demonstrate where the limits of their credibility lie. We have done this, though. We have been concerned about the increase in greenhouse gases since the 1950s. The first relatively simple models arose in the 1980s. This is a paper that there's a figure from a paper that was published in 1981, which predicted what would happen by the year 2020. And in fact, the warming has been larger than what was predicted in the 1980s. The first GCM, the first complex physics-based model was for transient, was done in 1984. And there again, the estimates of the warming that you see are actually compare very well with the warming that we've actually seen. We keep doing this. In 2000, we did a more expansive, more multi-model, more international estimate of what the changes would be from 2000. And again, what we find is that the model estimates from 2000 have actually matched what we've seen in 2000 up to 2016 quite well. We did it again in 2005, and the answer is the same. We're about to do this again, and in another 10, 20, 30 years, we'll be able to assess how much better our models are getting. But the fundamental thing to take away from this figure is that the basics of why the planet is warming have been understood for 30 years. So what does this mean for the future? Now, I'm not a soothsayer. I can't tell you what brilliant inventions the engineers will come up with. I can't tell you how societies will organize themselves. And so what we do is we take scenarios, storylines that involve big decisions that are made by the community as a whole. So on the left, you've got aggressive mitigation. That would be an effort that seems rather optimistic at this point to really reduce emissions starting from before now and reducing emissions to effectively zero by 2050, and then negative emissions subsequent to that. That is a very optimistic scenario. And in that case, you can see that the planet will warm, another 1 or 2 degrees beyond what we have seen. On the right, we have business as usual. And when I say business as usual, I'm talking about our ambition to burn everything that we can find, to burn all the coal, all the oil, all the natural gas, all the tar sands, all the other things that are going on. And that change, I'm sorry, I have to hold on just a second. Oh, apologies, childcare emergency. And that is a very pessimistic scenario. And something that might be realizable is the serious mitigation scenario. So that's a scenario where we make efforts, but they're not as strong as we could make them. Now, the temperatures that you're seeing here, the red, that's around 4 degrees Celsius warmer than at the beginning of this century. Now, 4 degrees Celsius is about just under 8 degrees Fahrenheit, and that is that full ice age unit that I mentioned. The changes under a business as usual scenario will be a completely different planet. Even the changes under serious mitigation, you will see, for instance, in the US, you're talking about annual mean changes of over 4 degrees, over 8 degrees Fahrenheit, summertime changes a little bit less, wintertime changes significantly more. Changes in the sea ice in the Arctic are such that even under serious mitigation, there will be no summer sea ice in the Arctic. The consequences for sea level will range from perhaps 3 feet to conceivably many more feet than that. And that has serious, serious implications for coastal infrastructure. Now, I'm obliged in all of my presentations to include a picture of a polar bear. This is one I actually took myself, and it wasn't quite as close as it seems. Because people think of animals as being affected by climate change, and people think about polar bears. But in fact, the biggest impact that is going to affect humans is not what's going to happen to charismatic megafauna, however cute they may appear. But it's maybe going to affect creatures like this. Some of you might know what these are. These are larvae of pine bark beetles. And it turns out that those beetles have a temperature sensitivity, which means that if it doesn't get cold enough as they're building up their winter resilience, they will breed much, much faster than they're used to doing. And we've seen the consequences of that across the West, across the Rockies, all the way up to British Columbia. Huge acreages of hillsides turn from green to brown dead trees in a season. Now, the outbreak there is climate mediated. And we don't understand how climate change as we progress will impact other ecosystems, other key species, other key disease vectors, all of which rely on temperature and water availability and humidity to go through their life cycles. These things are all going to change, and the more that they change, the more surprises we are going to see. Scientists are in a very odd position. This is a quote from Sherwood Rowland, who won the Nobel Prize for understanding the chemistry of ozone depletion. And he said, "What's the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is stand around and wait for them to come true?" And it captures the fundamental dilemma that we have, the scientists who are looking at this problem. For instance, last year, at the beginning of the year, I predicted that 2016 would in fact be the warmest year on record, as it turned out. Part of my brain, my scientist brain, at the end of the year when I was found to have been correct, says, yes, look how clever we are. We managed to pull information out of the real world, apply our theory, make a prediction, and have that prediction come true. Gosh, how clever are we? But then the other part of my brain, the citizen part of my brain, the normal human part of my brain, says, no, I don't want this to be true. I don't want the world to be warming at an accelerating rate. And we're stuck in this position where we are making predictions, and for 30 years, those predictions have proved correct in the large scale of things. And yet not one single person who is making these predictions want these things to be true. They will not be true if governments, societies, individuals, engineers find ways to reduce emissions that allow society to continue. That is a huge burden, unfortunately, to be putting on the next generation of engineers. But unfortunately, that's the way that it has ended up. The key thing to remember, though, is that predictions don't have to come true. The predictions that Sherwood Rowland made for the decreasing thinning of the ozone layer are not going to come true because we put in place bans on CFCs, we develop new technologies for refrigeration, and we are in a position now where the ozone hole is starting to repair itself, and the slowing and the thinning of the ozone layer in the tropics has slowed. We don't want our predictions to come true, but we're afraid they will. And so I'll just leave you with one more thought. Where we are now, we understand what's going on, despite the complexity. But the next chapters in this story, in our climate story, are still being written. And they're being written by the next generation of engineers and policymakers and scientists. And there is no more important problem to be working on. Thank you very much.